Every commercial jet you've flown on uses a turbofan engine, not a turbojet. Most passengers never notice this crucial distinction in aircraft propulsion technology. This engineering difference explains why modern airliners are whisper quiet, achieve long transcontinental flights, and changed aviation economics drastically since the original jet age. Both engines are gas turbines following the same thermodynamic cycle: air intake, compression, combustion, and exhaust. The key difference lies in what happens after the turbine. The turbojet was independently developed by Frank Whittle in Britain and Hans von Ohain in Germany during the late 1930s, arriving at nearly identical solutions simultaneously. The turbojet's concept is elegant: compress air, burn fuel, and eject the hot gas rearwards to generate forward thrust. This simplicity made it very seductive. Unlike propeller planes, turbojets feature no propeller, gearbox, or reciprocating parts, relying purely on momentum exchange of the exhaust gases. It's pure, direct power. The turbojet generates thrust by accelerating a relatively small mass of air to an extremely high velocity. Everything in its core serves this purpose. The core of a turbojet comprises essential components: compressor stages, the combustion chamber where fuel ignites, the turbine, and finally the exhaust nozzle. After combustion, hot gases expand through the turbine section, which then harnesses energy to power the compressor at the engine's front, sustaining the cycle. Turbojet engines were designed for optimal performance at high speeds and high altitudes, making them ideal for early supersonic aircraft and military fighters. Compared to turbofans, turbojets are lighter and more compact. This design characteristic made them highly suitable for aircraft where raw speed was the primary focus. An early example is the Rolls-Royce Derwent engine, which powered the Gloucester Meteor, one of Britain's first operational jet fighters during World War II. Another example, the Pratt & Whitney J57, powered the iconic B-52 Stratofortress, showcasing turbojet capabilities in large strategic bombers of the Cold War era. The Bristol Olympus 593, powering Concorde, represented the turbojet's peak, producing 38,050 pounds of thrust with afterburner, yet it was extremely fuel-thirsty. Concorde burned 25 tons of fuel per hour at cruise, illustrating turbojets' inherent disadvantage: low fuel efficiency at subsonic speeds and extremely noisy operation. The turbofan engine emerged as an advanced evolution of the turbojet, specifically designed for greater efficiency, quieter operation, and enhanced thrust capabilities. A critical feature is its additional bypass air system. This innovation dramatically improves fuel efficiency and overall performance, addressing turbojet limitations. Air enters the turbofan through a significantly larger fan at the front, encased within a nacelle. This large fan is a distinguishing characteristic from turbojets. Upon entering, some air bypasses the engine's core, forming the cold section. The remaining air enters the core, where it undergoes compression, combustion, and expansion. Ultimately, thrust in a turbofan is generated by both the high-velocity exhaust from the core and the accelerated air from the bypass duct. This duality defines its efficiency. The bypass ratio is crucial. It's the ratio of the amount of air bypassing the core to the amount of air passing through the core. This ratio dictates engine characteristics. High bypass turbofans, commonly used in airliners, feature large bypass ratios, often as high as 9 or 10. This significantly improves fuel efficiency. In contrast, low bypass turbofans used in fighter jets have much smaller ratios, typically in the 0.30 to 0.50 range, balancing speed and efficiency. The higher bypass ratio directly leads to greater propulsive efficiency. By moving a larger mass of air at a slower speed, less energy is wasted. Bypass ratio significantly impacts fuel consumption, noise levels, and overall performance. Turbofans are known for better efficiency and quieter operations. Initially, pure turbojets were favored for military fighter jets due to their ability to achieve very high speeds and offer a compact design for minimal drag. However, these turbojets had clear limitations for sustained combat. High fuel consumption drastically limited range and endurance for military missions. Furthermore, turbojets were notoriously inefficient at lower, subsonic speeds, crucial for many combat maneuvers, patrol, and loitering operations during missions. The need for better efficiency, range, and multi-role capabilities led military aircraft designers to transition towards turbofan engines for fighter jets. Low-bypass turbofans became the gold standard for fighter jets. They strike a crucial balance between high-speed performance and essential fuel economy. These advanced turbofans provide significant thrust for rapid acceleration and exceptional maneuverability, critical for air-to-air combat and evasive actions. Low-bypass turbofans offered superior thrust-to-weight ratios compared to turbojets. This meant more power delivered for less engine mass, enhancing overall performance. The increased low-speed thrust of turbofans also significantly improved takeoff performance, allowing shorter takeoff distances and higher climb rates for fighter aircraft. This improved performance offered greater adaptability, allowing fighter jets to perform a wider array of missions, from interception to ground attack, effectively. Ultimately, the shift to low-bypass turbofans was driven by the need for enhanced combat effectiveness, where raw speed alone was no longer sufficient. Today, most military jet engines utilize low-bypass turbofan designs. They combine critical advantages of both engine types for versatile operations. They perfectly balance performance needs, offering high thrust for speed and maneuverability, along with improved fuel economy for longer mission profiles. The evolution from pure turbojets to turbofans marks a significant, decisive engineering victory in the history of powered flight. It redefined aircraft capabilities. Engine choice fundamentally drives aircraft design. From airliners to fighter jets, the engine dictates optimal mission, range, speed, and endurance. According to Pilot Institute, the choice between turbofan and turbojet depends largely on the specific needs and objectives of an aircraft, emphasizing mission-driven design. To a student pilot, understanding engine types is fundamental. The aircraft's entire design centers around the job it is expected to do, informed by its engine. For concise understanding, turbojets are all-core, with fast exhaust, optimized for high-speed performance, but are characteristically louder during operation. Turbofans, however, are renowned for being more efficient, using less fuel, and delivering significantly quieter operations due to their bypass air design. While turbofans offer many advantages, their additional components mean they typically require more maintenance compared to the simpler turbojet engines. Fundamentally, both engine types represent similar mechanical systems. Turbofans have also benefited from decades of technological advancements, becoming extremely safe and reliable. Modern low-bypass turbofans in fighters often incorporate thrust vectoring nozzles. These direct engine exhaust for enhanced maneuverability, a key combat advantage. While excelling in efficiency, low-bypass turbofans still retain the capability for supersonic flight. They achieve this with afterburners, temporarily increasing thrust. The cooler bypass airflow helps to mix with the hot core exhaust, reducing the overall infrared signature. This is a subtle yet crucial advantage for stealth. For stealth aircraft, turbofan design allows for better integration of engine exhaust into the airframe, further reducing radar and infrared observability. Modern turbofans are key to the success of multi-role fighters like the F-15, F-16 and F-18, enabling them to excel in various combat scenarios. While largely superseded in frontline fighters, the turbojet's legacy lives on. It was a crucial precursor, paving the way for all subsequent jet propulsion advancements. The story of turbojets and turbofans is a testament to human engineering ingenuity, constantly pushing boundaries for faster, more efficient, and more capable flight. What does the future hold for jet propulsion? Hybrid engines, adaptable cycle engines, and other innovations continue to evolve jet engine technology for new challenges. The journey from pure speed machines to versatile, multi-role aircraft is a direct reflection of engine development, adapting to strategic and economic demands. Even for military applications, efficiency remains paramount. It translates to longer range, more time on target, and reduced logistical burdens for air forces globally. The combination of speed, maneuverability, and range provided by turbofans gives modern fighter jets significant tactical advantages in complex aerial warfare scenarios. As Aero Insider highlights, the high-bypass turbofan is one of the most decisive engineering victories in powered flight. Its impact is undeniable across aviation. The drive for innovation in jet engines continues unabated. Engineers constantly seek new ways to optimize thrust, efficiency, and operational flexibility. The journey from pure turbojets to advanced turbofans underlines aviation's commitment to continuous improvement, balancing raw power with smart, sustainable performance. From global air travel to national defense, these sophisticated propulsion systems power our modern skies, enabling feats of flight once considered impossible. What aspect of jet engines fascinates you the most? Share your thoughts in the comments below, and don't forget to subscribe for more fascinating engineering insights.